do this one in a couple of parts, but this is a tough section. This is the chemical basis of life. This is a really, really cool there's a technique to this, and it's really neato, but this is showing you just the cytoplasm. These are all the cytoskeletons, all little bits and stuff in it, so and the whole cell. And so we'll see this picture again, but it's really beautiful. All right, so some big ideas and concepts. So our essential question for this section will end up being, what are atoms, elements, and compounds? See how this works so lovely here? And then we'll just add on to it, and how do they bond? So that's your essential question. What are elements, atoms, and compounds, and how do they bond? So this section of what we're going to look into is we'll do water supporting qualities and stuff like that later, but these are the sections we're going to cover kind of this weekend. Okay, so let's take a look. Basically, when we get to the water part, this is going to be really interesting. This is going to be the part that we'll look at, but chemistry makes up a large portion of things because water makes up a large portion of our Earth. It's a big deal. So that's how that comes into play. So general introduction on this stuff. Chemicals are the stuff that make up our bodies, the bodies of other organisms, and the physical environment. So when I say it, I say chemicals are the stuff that make up stuff. Like all of it. Because chemicals make up all the inanimate objects, but in the case of biology, the study of life, chemicals are going to make up all the living things too. Life's chemistry is tied to water, which is why we talk about the earth and that kind of thing. All organisms require a body, and chemical reactions in your body occur in cells that consist of anywhere between 70% and 95% water. Isn't that crazy? So there's so much water to be had here. That's what's going to make that next section really important. But for now, in order to interpret what's going on in water, we do need to make sure that we understand the elements, the atoms, and the compounds as they exist. So this could be a review for some of us, and some of us will need some extra help on this. Do the best you can. Take some notes. See if you've got a... Alright, so to get started, organisms are comprised of elements, and then the compounds, because elements are in various combinations, and we call those compounds. So living organisms are comprised of matter. Matter is anything that has mass and takes up space. That's how I know. Careful with the weight thing. I'm going to cross this guy out for now, because mass is something different. Weight depends on gravitational forces, so you can think of it as weight, but mass is just a teeny tiny bit different. So matter, though, is anything that has mass and takes up space. Mass just means that it contains stuff, and we can look at an example of that. We'll do kind of a demonstration to make sure we've got mass. Okay. Matter is composed of chemical elements. An element is one of those dudes that you find on the periodic table, and you can't really break that down into any other substances. There are only 92 of those guys that actually exist in nature. Then the other ones, somebody chemically formed in a lab. But they work. So here are some of the elements. These are kind of the big ones that we'll talk about, kind of the big four of the body. Oxygen, obviously. I mean, think about inhaling, right? And even, I mean, think about this as it makes up water. So this is a large part of water. Carbon is going to be in the foods that you eat. So when you eat any kind of glucose, sucrose, sugary stuff, and carbohydrates, your proteins, everything else is going to have carbon involved with it. Hydrogen as well. Hydrogen makes up, there are a ton of hydrogen, but because they're so tiny and they don't have a whole lot of mass, they only account for a small percentage. And then nitrogen makes up a small percentage as well, and you get this mainly from your proteins. Just as a side note. Okay. You also have some other things. These are your kind of less, they're not trace elements, but these are your other elements that are important. If you look at actually a label, or you look at a multivitamin, these are going to be those things that are shown for multivitamins. Your calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium. Those are your other ones. And these are your trace elements down at the bottom. We're not going to get into those very much, but the big four that you need to know are carbon, oxygen, hydrogen, and nitrogen. Okay. A compound. So if you're new to this topic too, it might be worth it to, at least on a separate page, maybe start writing out some of these words that I underlined, some of the bolded ones, because we're going to make sure that we take some time to really look at vocabulary on this stuff, because I keep throwing it out at you and you need to know what it is. But a compound's a substance that just has 2 or more elements, so it's 2 plus elements. That's how I would write it. Okay? And obviously you'd probably put in the rest of the letters, but I'm working quickly. Okay, compounds are more common than pure elements. It's just the way it is. Mixtures, things like that. It's just, stuff is rarely ever pure. Okay, sodium chloride, that's your table salt. By the way, that's NaCl, is a common compound that's equal parts sodium and equal parts chlorine. Okay, there you go. So you have sodium, which is really, really highly reactive. You put that guy in water and you get like this boom explosion thing. Chlorine is a really obnoxious gas that will mess you up. Both of these things, very awful things, but you put them in an equal ratio, they make delicious, delicious table salt. So yay for chemical reactions. 25 of those elements are essential to life, and if you're looking at those, that's essentially what? Your carbon, your hydrogen, your oxygen, your nitrogen, the calcium, the phosphorus, all that stuff down the list, and then the trace elements. So those are going to make those things up. Okay. Again, 4 elements make up 96% of the weight of living organisms, and those are carbon, oxygen, hydrogen, and nitrogen. These are essential but only needed in minute quantities. Those are your trace elements. You just need a teeny tiny little bit of those. A little bit. Some trace elements are required to prevent disease. So iron is one, but we can talk about hemoglobin. That's an important protein in your blood. It's weird, and it's going to look like there's 4 parts to it. It looks like this. I'd have different colors, but there you go. It's in 4 little weird lobe things, and right in the middle of it sits an iron. And that iron is absolutely essential for oxygen transport in the body, because an oxygen will hook up right there, and then they'll move, and it'll get around, and it'll be transported in the body. So this is a trace element that's super, super important. Okay. Also, things that are important, like iodine deficiency prevents production of thyroid hormones. Lack of iodine. So having iodine prevents the production of thyroid hormones, causing goiter. So this is goiter. If you look at her thyroid, it's massive. This is not pleasant. So she has goiter, and that's due to iodine deficiency. Eye deficiency. Okay, there we go. So some connections on this. Trace elements are common additives in food and water. So one of those things is fluoride. It's added to water, and it's added to dental products, and it helps make your teeth super white. This would be the best way to show that. So fluorine is for this stuff. But less creepy. Okay, so it's added here as well. Fluorine is an additive. It's, in small quantities, it's really, really good for your body. It's not going to do anything bad for you. In fact, it'll just help. Okay. Several chemicals are added to food for preservative sake. It depends on whether you're into that. Things can be added for a nutritional value, like ascorbic acid. I'll put the old term. This is ascorbic acid. That's how I always wrote it. It's just vitamin C. You can add that all over the place, and that gives you a nutritious value. Okay. It also helps things look better. if you're ever curious about any of this stuff, there's a biological thing that also works for nutrition and dietary purposes. Always read your nutrition facts. They're always there. Right? And this is some of the stuff we're talking about. So you can look for some of these trace elements. So you get calories, which is a weird descriptor anyway for some of this stuff, but whatever. Okay. You can look up fat contents, cholesterol. That's a different goofy looking molecule. That's one of your steroids. There's like sodium, potassium, things we talked about, carbs, these macromolecules, proteins, and other macromolecules. Then they'll list calcium, iron, let's see, phosphorus, magnesium, zinc, and copper. I'm trying to pick out just the elements for you. Then you get other molecules like A and C and vitamin D and riboflavin and niacin and B and folic acid and B12 and blah, blah, blah. Okay, so there's an endless amount of stuff that you can add to these things in order to make them more nutritious, right? Make them total whole grain. Where's... Oh, they didn't give you the list here. I was going to see if the first ingredients was whole grain. Probably not important at the moment. Okay. But, so some other just relative facts, and I know I'm moving slightly faster than some of you might like, but that's what the pause button is for. I don't know where yours is. I think you can just hit the screen. Mine's down here. Okay. But you can always hit pause. All right, so an atom... worth knowing. That's the smallest unit of matter that still retains the property of that element. And we usually represent those, like my favorite one to represent, because it's so easy to draw. Here's hydrogen. So this guy in here is your proton. Sorry, I didn't mean to draw that. And this right here is your electron. That's it. That's all that's in a hydrogen. Just a proton and a lowly electron. And you can have a whole bunch of these in an area and it still makes hydrogen. Okay. It's the smallest unit that makes up one single element. Okay. Three subatomic particles are relevant to our discussion, right? We've got protons, electrons, and neutrons. It's a good time to pause it. You can, if you're forgetting, you can cover it up real quick. But protons are always positively charged. Electrons are negatively charged. Hello. I'm awake still. All right. And the neutrons are neutrally charged. So these are our charges for each of these. Okay. That should be intuitive, but make sure you know that. Neutrons and protons are packed into the nucleus. Oops. Okay. Let's think about helium's a good one to think about. So here's my dark ones. These are going to be protons. Then I've got these other things here, and those are both neutrons. So protons and neutrons are found in the nucleus, and then orbiting around it, you would have your electrons. And that would be helium. Okay. So you always find the negative charge around the outside and the positive charge in the nucleus. Positive nucleus. Okay. Electrons orbit the nucleus. There you go. So here's a better description of helium and a much better drawing than what I just gave you. But you can see the two positive charges here, and then these are your two neutral guys. I usually give them kind of a 0 there, but they're neutrals. And then you've got your two electrons on the outside. Okay, so what gives you the mass number? I'll tell it to you like I tell everybody else, because we think about it. We say, okay, well, how do we get the weight from this when we've got electrons out here? How come they don't weigh anything? Well, the electrons, they're kind of fast moving. They're kind of different. They're kind of small and something else. So I always compare it to, you have a particular mass yourself, and sometimes things happen. If you were to shoot, it would not have any impact on how much you weighed. So this is just, remember, this is a comparison here. It's almost like a cloud of gases around it. It has no impact on the weight of what's in the middle here. Okay, so this is the mass. This is kind of, the gaseous smell around it. All right. That's how I think of it. So they have no weight. So the only things that you're counting for mass and atomic mass units are just the dudes in the middle. So we have 1, 2, 3, and 4. So that gives us a mass number of 4. The electrons are negligible here. They don't contribute at all to the weight. Okay. The number of protons is the atomic number. If you guys have not had chemistry yet, this is worth knowing. We'll make sure that we diagram out one, a little bit for us later. But the atomic number will always give you protons. Mass number is going to give you the number of protons and neutrons. So use some math skills here. If I've got mass number, which is protons and neutrons, and I have atomic numbers, which are just protons, how on earth do I find the neutron number? Think about it, think about it. Mass number minus atomic number. That will give you the number of neutrons. Yay! Okay, simple math. Ta-da! And the atomic mass, as you can call it either way, but the atomic mass is approximately equal to the mass number. It's more of an average, but that's something you can explore a little bit more in chemistry. Okay, so here we go with carbon, another super awesome one to look at. Here's carbon, electron cloud. We don't care what's going on in here. We want the mass strictly from here. So if we've got protons and neutrons, it looks like there is 1, 2, 3, 4, 5. But there must be another proton hidden back in there somewhere because it needs 6. Okay, and we got 1, 2, 3, 4, 5. So there must be another proton or a neutron hidden back there because there should be 6 and 6. When you add those guys together, you get a mass number of 12. Okay, that's how that works. But if we just have, let's see, and I'll give you this. The atomic number is 6 too, so if you're looking at the periodic table, it's somewhere at the top. Sometimes it's in a little box, but it's 6. That's the number of protons. Protons, mass number is protons and neutrons. That's how you figure that out. Just so you know. All right, so that's general basic stuff. I would look at a periodic table. Let me maybe go back for just a second. Yeah, I'll go back here. I'm going to draw you one out to look on the periodic table for. It's worth looking at and make sure that you know it. But where you can find basic information in case you forgot is that's the atomic number. Put AT number for short. This would be the chemical symbol, so that's for carbon. You usually get the atomic number, which is like 12.0 blah blah blah. It's an average, so you just have to forgive it, but it's going to round to whatever that mass number is. Okay, and those are kind of some of the things you're looking for. Some of them give you more detail or not, but this is where you find generally atomic number, and this is where you would find mass number or atomic mass. Either way, you find mass of some sort down here at the bottom. Okay. So look that up. ptable.com is a really good one to look at and make sure you explore it and kind of find some things out about the elements. But now that we've got a general idea about regular elements, we're going to start messing with them a little bit and see if we can get through that. So I promise some of the later sections are a little bit shorter, but we are going to get through these. And I'll get through 2.3 and then you can take a break and that'll be kind of your halfway point on this. All right, so although all atoms of an element have the same atomic number, they can differ in mass number. Mass number. Remember, atomic number is protons. So I'm going to put a little plus sign here because you can have the same amount of protons and differ in mass number. So if my protons are the same, but my protons and neutrons have changed, that's going to mean that the number of neutrons is different. Okay, so an isotope is a thing that has the same number of protons. So we'll say same protons. I'll circle that one. But different neutrons. That's an isotope. Okay. Atomic number is the same. Mass number is different. So we give it just a slightly different, we can think of it as weight. Right? Different isotopes of an element behave identically in their chemical reactions. So one that I'll look at, kind of a good example here, is when we put these things up top, just go with it for right now, but carbon can have either 6 neutrons or it can have this kind of other variation that has 8 neutrons. There are some others in the middle, but Just go with it. All right. These are some different variations. Now, just because I have 8, I have 2 more of those neutrons, does nothing to change the chemical reactions. Carbon-14 will still, in essence, behave just like carbon-12. It's not entirely accurate, but it's not worth talking about right now. Okay, but the general point is if you change the number of neutrons, you do not change reactivity. Why is that? Because it has no charge, right? There's no charge on this. Charges are what make things reactive. P.S. It's usually electrons that make things change, but if I change something that doesn't have a charge to it, it means that not a whole lot different is happening. Okay, just keep that in mind. All right, and that would probably be this. That would be worth knowing. All right, there are also these things called radioactive isotopes. Those are always fun, and it means their nucleus decays spontaneously, giving off particles and energy. And I can show you a really great video on this one, or you can look it up. It's like a radioactive isotope cartoon. You can always remind me about this one because this is one of my favorite videos, hands down, like all time to play. It looks like an old Looney Tunes cartoon, but it shows you how radioactive isotopes work and how they kind of decay and what happens. It's pretty great. Looney Tunes should be in everything. All right, so here you go, isotopes of carbon. Just to note, same reactivity. Still same ability to form a reaction or not form a reaction or whatever it is they're going to do. Okay, same reactivity. But you notice that the mass number is 12 because protons and neutrons are the same. Mass number of 13, well, now we just have one more neutron, and so when you add those, you get 13. Carbon-14, mass number is a little bit higher. We've got 8 neutrons, so that totals 14. P.S. If you've got a neutral element or neutral atom, your protons and electrons will always be the same. That's just a side note. But as far as isotopes are concerned, what we're really concerned with here is that protons are the same all the way across, but neutrons can change. Some of them you'll see that the number of neutrons may be less, but it doesn't matter. It just means that we can change the number of neutrons and it has the same reactivity. All right. Radioactive isotopes can help and harm you. That's true. Let's see if we can do this one. This should not take that long. All right, living cells can't distinguish between isotopes of the same element. If they have the same reactivity, we just can't really tell. So there's, it just doesn't work as well. So some radioactive compounds and metabolic processes can act as tracers. You can find some things. Think about if you're getting an MRI or something like that, so you're going to the doctor and you're trying to double check and see that parts of your stuff is okay, you can actually have some of these elements become tracers, and they'll kind of trace their way through a pathway, and we light it up on the old X-ray and go, oh, there it is, or the MRI or the PET scan or whatever. We can look at it and we can trace its behavior and see what your body's doing. So it's really fascinating. Radioactivity can be detected by instruments. How fascinating technology has gotten, just as we talked about. Using those instruments, the fate of radioactive tracers can be monitored in living organisms. Some of my favorite radioactive things are when you can make a mouse glow because you're tracing a certain, there's a stem cell thing where they trace it and the mouse glows. We may have to look at that. This is a terrible thing when I find a lot of videos that I like, and then I'm just like, let's watch videos. But we're not doing that. We gotta also do experiments, so get over it. You can also find these videos on your own time. They're really, really cool. Radioactive tracers are frequently used in medical diagnoses. Like I said, they're involved in MRIs and PET scans and CAT scans and whatever else they use them for. And you use those imaging instruments like the MRI, the PET scan, or the CAT scan to detect them. So if you're wondering what the PET scan is, that's a positron emission topography. Yeah, that's a mouthful. All right. It'll just detect the location of injected radioactive materials. That's all its purpose is just to be able to view the location of injected radioactive materials. And it's really good for diagnosing things like heart disorders, cancers, and brain research. Okay. I'm just giving you the application also to some of the radioactive isotopes. The fact that we have to learn this chemistry junk is for a purpose. So that's all that is, I swear. We'll talk about that, but there you go. So here's an example, and you can do these wonderful things with, that's a PET scan, and you can actually see these really cool images of the brain. That's how we get those really rad images of the brain and what we're looking at. So you can find a tumor, or sometimes they can trace things and see where the brain's active or not. It's neato stuff. So, oh yeah, here you go. Here's another example. If you're looking for Alzheimer's, you can look at a healthy person, and this is what brain function looks like. And this is kind of the chaos that is Alzheimer's. So it's like, what is your brain doing? That's why people with Alzheimer's tend to forget a lot, things like that. There's a lot going on with the brain there, and you can detect that there. All right. In addition to benefits, there are also some dangers. Uncontrolled exposure can cause damage to some of the molecules in a living cell, especially DNA. DNA and radioactive isotopes do not get along very well. They don't. They get along like Grumpy Cat and everything else. They just don't get along well. Chemical bonds are usually broken when emitted energy can cause abnormal bonds to form. So that's a reiteration of DNA and radioactive isotopes just do not get along. I'll put radioactive isotopes for short. So they do not always like each other. Okay. I will stop it here so you can wrap your brain around it. Make sure you understand that before you go forward, because Lord knows you do not want to go on to chemical bonds before you understand the chemicals. If you have to, go find yourself some Khan Academy or some Crash Course is really fun for some of that stuff. Double check those and see if that helps you kind of explain some of the material. And when you're ready, we'll start with chemical bonds.